NASA's latest robotic lander, InSight, descends to the surface of Mars. A challenging effort greeted with elation.
Touchdown confirmed.
Meanwhile, an orbiting ESA satellite, ExoMars, begins its own exploration of this enthralling planet. The majestic stereo imagery of Mars as seen from orbit reveals a planet of dynamic texture and form, slowly revealing its secrets.
We've sent a lot of missions to Mars in the past. We've sent rovers, we've sent orbiters, they've done a lot of really great science and a lot of really interesting measurements, but those measurements just scratch the surface of Mars. We know a lot about the surface of Mars, we know a lot about its atmosphere, and even about its ionosphere, but we don't know very much about what goes on a mile below the surface, much less 2,000 miles below the surface down to the center. And this will be the first mission that's going to Mars specifically to investigate the huge extent of Mars below the surface. The basic idea of InSight is to map out the deep structure of Mars for the very first time. We're going to map out the thickness of the crust, the size of the core, the composition of the mantle and core of the planet, sort of get the first map of the deep inside of Mars. It's going to Mars to do the science, to make the measurements that scientifically and personally I've been waiting for over 30 years for. As a graduate student, I was doing research on Mars, and I just needed to have the thickness of the crust. I just needed the thickness of the crust, and we didn't have it. And seismology was the way to do it. And so I thought, well, maybe someday somebody will put a seismometer on Mars and get this measurement so I can do my research. And so it's kind of an amazing journey for me to look back and say, I'm the guy who's actually going to put that seismometer on Mars, get that information, and now I can go back and finish the job I was trying to do 30 years ago. It's an amazing feeling.
The InSight mission will finally provide seismic information of Mars that scientists have been wanting since the very first Mars lander, Viking. It had a seismometer on it, but for a variety of reasons it never got back any seismic data. There's been many other attempts to get seismometers onto the surface of Mars for very good science reasons, but they've, for one reason or another, never been successful. So now we're right on the very edge of getting a seismometer onto Mars that will finally give us back seismic data. That seismic data is incredibly important to scientists because it gives them an idea of what the size of the crust, the mantle, and the core are, as well as the properties of each of those, which are the basic internals of every rocky planet.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch
on mobile devices or the big screen. All for free. No subscription required.
The most fun or interesting thing about InSight from an engineer's point of view is really that we're playing the claw game super far away on Mars. We're taking this grapple and we're going to pick up an instrument and lift it up off the deck and put it down on Mars. So I like to say that we're playing the claw game on Mars with no joystick.
Next, a wind and thermal shield will be lowered over the seismic instrument to protect it from the environment. The second instrument, the heat flow probe, will be placed on the ground and over time will hammer itself down to take subsurface readings.
There's a lot of international partners on InSight. It really takes a whole world to produce an exciting mission like this. So most of our science missions are actually being supported by our international partners. So for example, the SEIS instrument, our seismometer, has support from the French, the Germans, the Swiss, the UK folks. So we have a variety of those people. The heat flow and physical properties probe is being provided by the Germans with some support from Poland.
InSight is a mission to Mars, but it's much, much more than a Mars mission. In some sense, it's like a time machine. It's measuring the structure of Mars that was put in place 4.5 billion years ago, so we can go back and understand the processes that formed Mars just shortly after it was accreted from the solar nebula. By studying Mars, we'll be able to learn more about Earth, Venus, Mercury, even the Moon, even exoplanets around other stars.
ESA's Trace Gas Orbiter mission arrived at Mars some time ago. Since then, this 3.5-ton spacecraft has been gently brushing the atmosphere to gradually adjust its orbit. In ESA's Planetary Missions Control Room in Darmstadt, Germany, flight controllers have been checking systems and commissioning instruments on the ExoMars Trace Gas Orbiter. Now it's ready to begin its science mission.
It has been a long time since we arrived at Mars in October 2016, and we have had a very long period, 1 year, of aerobraking, which consisted in reducing the orbital period from the time when we arrived, where it was actually several days, to 2 hours, which is the nominal period for science observations. I'm looking forward to the next few months enormously because the TGO will finally be able to show its full capability, the full capability of its instruments in terms of accuracy and the quantity and quality of data, pictures, spectra. And also because we will be able to do joint observations with our previous spacecraft at Mars, Mars Express, which is still alive and working after 15 years, actually. And for ESA, having 2 spacecraft around Mars in complementary orbits from a scientific point of view is very exciting and will allow certainly some very interesting discoveries and observations.
ExoMars will fill a double role when its partner rover is dispatched to Mars in the coming months in the search for life on the dusty planet.
It is a communication satellite on top of being a science orbiter. The so-called relay function allows us to communicate with all landers and rovers on the surface of Mars. At the moment, there are only rovers and landers from NASA, Curiosity and Opportunity. Some tests had been done already soon after arrival at Mars. And now we are going to start a campaign to calibrate and determine the best performance to relay data.
The Trace Gas Orbiter's primary mission, however, is to identify gases in the Martian atmosphere, particularly methane. First hinted at by Mars Express, and then by NASA's Curiosity rover as it sniffed the atmosphere with special sensors.
Well, we know that the lifetime of methane is very short, just a few hundred years. It will be broken down by the sunlight, by the UV ultraviolet component of the sunlight. So if it is there now, we know that it has to be refilled all the time. And where does it come from? That's the big question. It cannot be synthesized really in the atmosphere. It has to come from the surface or from the subsurface. But what are the processes that produces it? This is what we want to find out. One possibility is that it is some geological reaction between minerals and water. Another possibility is that actually also are microbes down buried underneath the surface that is producing it today or has produced it a long time ago, and they're all dead now, but that the methane has been kept underground and with some mechanism is released to get up into the atmosphere. So these are all these kind of things we try to find out.
By using the orbiter's powerful spectrometer, scientists hope to discover whether the methane comes from a geological or biological source. 95% of methane on our own planet comes from living organisms. The ExoMars rover, landing in 2021, will drill up to 2 meters beneath the surface to search for this evidence of life. And the rover, as well as NASA rovers and landers, will use the orbiter to keep in touch with Earth. Mars exploration is an international endeavor, and every mission adds to our understanding of this alien world, a place that some of us might someday call home.
Planetary exploration is always very exciting, but Mars, of course, has this very special thing, is that there is actually a place that you can imagine yourself walking on. You eventually, within not too far in the time in the future, surely people will be walking on Mars. And that makes it very exciting. And then to think about this idea that there might have been some kind of life, or even exist today underground on Mars, that makes it a very special place.
Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM.
Well, the SAM instrument detected a variety of organic molecules in a sediment that is from an ancient lake bed in the middle of Gale Crater. And what's important about these is that we now have a lot more certainty that there's organic molecules preserved at the surface of Mars. We didn't know that before. But what's interesting is that we don't know what the source of these organic molecules is right now. There's just not enough information from that. However, if we drill deeper and we look around a little bit more, we might actually be able to get to that information and tell, did they come from life? Did they come from geological processes? Or maybe they were from meteorites that were deposited in the lake. We just don't know right now, but hopefully we'll figure that out.
Curiosity is searching for carbon-based organics.
SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria.
Some other organics have been detected, like thiophene, which contains sulfur. Introduced by geological processes, this sulfur acts as a preservative, binding organic molecules together and making them resistant to oxidation, so preserving them for millennia.
Organic molecules could be the food for life, or they could be the product of life, or maybe they're from something altogether different, such as geology or meteorites that were deposited into the lake. We don't know what the source is, but there's a story there, and we're going to uncover what that is.
Scientists still don't know if the discovered organics on Mars are biological in origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. So for a time, Curiosity continued to travel, find interesting outcrops, drill holes, take samples. Then, inexplicably, something went wrong.
The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's two stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck.
With Rover 2020 design and construction well underway, engineers will be sure to avoid such a problem with Curiosity's cousin, which will land in the Jezero crater in 2020. "2020 will be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos are sending the ExoMars rover to the Red Planet. Rover 2020 and its companion helicopter will no doubt expand our search for life, past or present. However, the big advance forward in organic analysis will be the game changer. Both rovers will carry on board a MOMA.
The Mars Organic Molecule Analyzer, or MOMA, is the largest and most complex instrument on the rover. Its mass spectrometer subsystem and its main electronics were built and tested at NASA's Goddard Space Flight Center, which also contributed mass spectrometers to NASA's Curiosity rover and MAVEN orbiter. MOMA is designed with a mix of proven hardware and innovative new technologies. Here's how it works. In gas chromatograph mode, crushed Martian rock is put into an oven and heated to 900 degrees Celsius in just 2 minutes, vaporizing the sample. Molecules of hot gas rise up and flow into a narrow 20-meter-long tube. Special coatings inside the tube cause molecules with certain chemistries to slow down more than others, separating the mixture of molecules over time. Next, a beam of electrons ionizes the molecules, giving them a positive electric charge and deflecting them towards the linear ion trap. The ions are caught by a fluctuating electric field and sent to a detector to determine the chemical makeup. While gas chromatography has been used to study Mars since the Viking program, MOMA has a second method for preparing samples that has never been used on another planet. In laser desorption mode, a sample is placed beneath a powerful ultraviolet laser. A beam of energetic light builds within the laser and fires in a billionth of a second, concentrating its energy onto a spot smaller than a grain of sand. This rapidly vaporizes a portion of the sample, releasing large organic molecules that could be broken down by oven heating. The laser shot also ionizes some of the molecules, allowing the vapor to head directly to the linear ion trap. Neutral molecules are ejected by a vacuum, while the remaining ions are sent to the detector to determine their chemical makeup. Laser desorption will enable MOMA to detect long molecules like lipids, the building blocks of cell membranes, a leap forward in the search for life on Mars.
The question of life on Mars is among the most important in planetary science, and the evidence may be buried just below the surface. With the help of MOMA, we will take one step closer to uncovering the answer. These images will pave the way to a new understanding of life in our solar system. Cubesats. They've been around for a while now. The domain of universities and institutions wanting to teach and gain experience in space. They're low cost, light, and very adaptable. Not only that, but they're also easy to send into orbit. Now, business is eyeing off these microsatellites with big plans for the future. The traditional satellite is an industrial and technological marvel. Designed and built from the ground up for a specific purpose with a long life expectancy, some communications and global positioning satellites are built on an off-the-shelf platform design to help alleviate costs. Launching them into orbit, however, is no easy feat. Weighing as much as 50 tons, they have to be placed in a geosynchronous or high polar orbit, which requires expensive launch facilities. The CubeSatellite or microsatellite, devised as a training and development tool for university students, has now taken on a life of its own as a low-cost alternative to the conventional satellites in particular roles and for new purposes not previously considered.
A CubeSat is a nanosatellite basically in a box size. Standard dimensions of a CubeSat would be 10 by 10 by 10 centimeters, and you can have multiples of that unit. So you could have a 3-unit CubeSat, for instance, 10 by 10 by 30 centimeters, and all of the satellite equipment has to fit inside that box. The origin of CubeSats goes back over 10 years. In the US, university professors were looking for ways to allow their students to essentially build and fly satellite hardware during their degree courses. And so that was envisaged as a very low-cost way for universities to get their students well educated in the engineering skill.
University student teams from around Europe have been busy in the last months making the final preparations for ASIO, the European Student Earth Orbiter. ASIO is preparing the space workforce of tomorrow. The student teams designed, constructed and tested the essential parts for the mission.
During its whole project life cycle, ASIO engaged several hundred students, and already before launch we can say that it achieved all its main educational objectives.
Launched aboard a SpaceX small satellite-dedicated Falcon 9, ASIO was released into a polar orbit. Aboard the satellite there is a radio amateur communication system by the University of Surrey and AMSAT UK in the United Kingdom. This enables ASIO to transmit real-time data to schools and universities for science and engineering lessons.
I participated in the LMP project. It is a bit a personal project for me because there is a component which I helped in the design, and I wrote my thesis from this component.
I've been involved in the development and testing phases of the power distribution unit of the ASIO satellite. It's an amazing feeling that your device will go up into space and it's ready, it's working well, and I'm so happy.
ASIO is a complex system, and in the end I think it was challenging activity for all the payload teams. We had the chance to stay with them. We had the chance to teach them a few things that typically are not so common in academia.
ASIO gave us the competence to actually build any scientific instruments here in the observatory. It gave us both the competence and also the connections with ESA, and we learned a lot from the projects in order to develop our further missions.
There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
where else could CubeSats be applied? A major space mission to Mars, InSight, was a perfect opportunity to test out some new technology.
Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites and generates more than 860,000 pounds of thrust.
Flying with the InSight spacecraft to Mars were two CubeSats. Called Mars Cube 1 or MARCO, they were a technology demonstrator and the first use of miniature modular CubeSat spacecraft design in deep space. The pair of briefcase-sized spacecraft, MARCO A and B, were launched on the same rocket as InSight and traveled independently of the main craft. They carried a number of communication and navigation flight experiments. Although NASA emphasized the experimental nature of the CubeSats before the InSight landing, the MARCO spacecraft performed as intended, receiving the UHF telemetry from InSight during its entry, descent, and landing phase, and rebroadcasting it at X-band frequencies received by NASA's Deep Space Network. This vindicated CubeSats as another tool in the exploration of deep space. To top it off, MARCO B managed to take a photo of Mars and transmit it back to Earth as it passed by the planet. The rush to exploit CubeSats is on. Scientists and engineers have begun designing, building, and launching various designs for specific missions and for testing new technologies in space. Rocket launching companies have been quick to respond, developing and flying dedicated launches for the emerging small satellites market. SpaceX and ESA's Vega launchers are among these companies, while the Electron from Rocket Labs has already begun flying commercial CubeSat launches and is planning a monthly service.
My involvement goes back 10 years from when I was working in the education office at ESA. So indeed, I was responsible for managing university CubeSat projects that we would then later fly on the maiden flight of the Vega launch. We had 7 CubeSats that flew on the Vega maiden flight, and actually many students were involved in those projects, and they went on to graduate, and many of them formed their own spin-off companies, which now forms the basis of the CubeSat industry today. What we're seeing is that the same technologies that are being exploited terrestrially for aerial drones are also being exploited by CubeSats. So I like to think that that same technology will enable CubeSats to become the autonomous drones of the space domain. With the capability of CubeSats to become autonomous space drones, they will have the performance to be able to perform autonomous navigation, close proximity operations around other target objects, and also be able to fly in swarm formations. So these are very advanced architectures. We might also see them being able to perform autonomous rendezvous and docking together, forming building blocks to build up larger structures in space in the future. When we do the CubeSat projects, of course, the standard engineering approach combined with the access to ESA facilities and technical know-how gives an added value to ESA member states to ensure that we maximize the probability of mission success within the tight financial constraints of each project. So far, we've flown one technology CubeSat in orbit, GOMX-3. That mission has been very successful. It's recently re-entered the atmosphere, so the mission has been completed successfully. Now we are preparing to fly another CubeSat called Carmen. It's designed to demonstrate re-entry technologies, a very exciting and challenging project. And beyond that, we have another 4 technology CubeSats in development, and we're already talking to our member states about starting many new projects in the future for these technology demonstrations.
The use of microsatellites for commercial and industrial purposes is a growing field of interest, as is the concept of the Internet of Things. One company has combined the two into what may become the next great technological revolution. Alongside household names like Microsoft, Google, and SpaceX, you may soon be adding Fleet to the list.
So Internet of Things is a concept that probably started 5 to 10 years ago. You know, people were talking about this. There are 25 billion devices coming online in the net. It's the 4th industrial revolution. Everything will be connected. It's going to change our lives. I kind of separate the concept in 2. The smart cities. So when our life will change into buildings, you know, your Fitbit connected to your fridge and your car driving itself, and smart fridges, smart traffic lights, and so forth. And also smart industry. So what happened in remote areas, in a big farm or in a big oil and gas company, a big mining, that's a heavy industrial revolution. So Internet of Things is the idea that we are kind of changing the way we operate. We have spent 40 years connecting people and, you know, bringing computer inside factories, and suddenly everyone has got a computer that cannot live without it. You know, if there's a day you cannot use a computer, you go home because what am I supposed to do? So in the next 40 years, things will change the industry in the same way the computer did. So imagine a big farm suddenly everything will be connected, from the soil to the literally soil, content to animal tracking, weather station, thousands of sensors that we allow the farmer to literally understand so much of the way they operate that we will solve the biggest problem on Earth, water leakages and drought and so forth. But that goes into, transport and logistics, not measuring pallets and fruits traveling all over the world. I think we waste 60% of our food in supply chain. So there are big changes happening, and this is all about little sensors being connected. The problem is that this big industry that I'm mentioning, they have not 3G. I mean, 3G, 4G, even 5G covers the population, but 95% of the world is unconnected. And this is where our farms are, where our mining and oil and gas company are, where the shipping containers are. So it's a kind of a problem that terrestrial infrastructure cannot solve. And well, we got space, or we solve it from space.
The potential for a constellation or swarms of CubeSats to become powerful research and communication tools is now starting to be explored. The ability to track almost anything across the planet is now a reality. The possibilities seem almost endless.
Internet of Things is interesting because with one satellite in LEO, so low Earth orbit, you cover almost every side of the planet. And customer sees you once a day. It's not much. It's not really good for high-speed internet or talking Skype or checking YouTube, but it's great, for a valve, or a soil moisture sensor, or a cow. You don't want to know where a cow is every single minute of your day. Probably you do, but once a day is perfect for LEO. But when you reach 100, or for us it's 100, it probably will be even less, the latency is so good that you can actually tackle some high pressure emergency applications, like safety and security, in which you want to send the data and grab it straight away and send it to the customer straight away. But the good things of Internet of Things is that you launch one satellite and then you're in operation. You can serve everything now. So we had launched 4 satellites last year. It was a great journey of fleet. For a startup, we launched them in 24 days. 2 with Rocket Lab was first Rocket Lab launch of nano satellites was commercial. So it was literally like, what is going to happen here? And then of course SpaceX and PSLV. But the first satellites we built was almost 1 year. The second one 2 months. When we launched with Rocket Lab, by the time we start building the satellites, to the time we booked the flights and the time we were in space, was 4 weeks. So there's a big revolution also on the launcher side, that can put us in space quite fast.
This startup company seems to have hit the nail on the head. Low-cost terrestrial sensors can be hooked up to almost anything, and their status uploaded to the CubeSats for transmission to the clients via the net.
The people that are booking these sensors, they come from the biggest oil and gas company in the world with all the farms in South America. This is big customer. So we are entering a phase in which, as most startups are starting so little, is having massive customer impact. That satellite company that operates for $1 billion in many, many years don't have. So it's time to see at these satellites and understand it's not a game anymore. This is going to be $1 billion companies very, very fast. So it's quite exciting.
This system could increase efficiencies and save waste across the globe.
Earth needs help. Earth needs monitoring. Earth needs efficiency. Earth needs water to be saved and food to be not wasted and people to be safe. So millions of sensors going to change the world forever. It's going to be billions. When we started Fleet, we started with a dream of connecting the entire world and millions of devices. We call it 1F. It's our first constellation, and For us, 2F is going to be the Moon, and 3F is going to be Mars.
The potential for space exploration is exciting. Quick and efficient data networks dispatched to the Moon, Mars, and beyond, or even swarms of CubeSats surrounding an asteroid or a spacecraft during rendezvous, sending back data and video. The scope is limitless.
Imagine you can have a constellation to track every robot and things just to make sure where they are, and this is just the beginning. You know, and the reality is that when you know, the big entrepreneur will go to Mars, they will put so many things, and you want to make sure they're tracked, and it's a complicated exercise. And a CubeSat, it's a way to go there fast. You know, when you need to move a big satellite to Mars, it takes a long time, and you launch a storm of bees. Eventually, they will get there. But eventually, we'll go there, and we will have to do the same. You know, we will have to have big responsibility when we start conquering the other planets, monitoring what happened. I think, yeah, it's going to be fleet responsibility as well, I guess.